And I'm going to start by talking about something called a binomial distribution. Okay, so we're going to open up this document, which is called binomialproblems.dox. Okay, you'll have that on your, you'll be able to access that from Blackboard as well. Okay, and I'm going to start out by opening up an Excel file. And first problem that I have here, a study indicates that 10% of nursing home patients are diabetic. You randomly sample 10 patients. What's the likelihood exactly? One will be a diabetic, two or fewer will be diabetic, more than four will be diabetic, or four or more will be diabetic. Well, let me think about this. I'm going to open up Excel. And you guys remember that we were working with with probability trees the last time we got together, where if I flipped a coin once, it was 50-50 chance of it being heads or tails, and then the second flip was again 50-50 chance of being heads or tails, and so on and so on and so on. And we noticed that if we presumed before we started flipping the coin at all, if we presumed that if we flipped the coin 3 times in a row, the probability of all three results being all tails or all three results being heads is going to be 0.5 times 0.5 times 0.5. Okay, that was pretty straightforward when we were talking about, like in this situation, if we were to sample 3 people from this population where 10% of the population is diabetic, we would randomly sample 3 people from this population. We would say the probability of all 3 people being diabetic is going to be 0.1 times 0.1 times 0.1. Okay, similarly, since 10% of them are diabetic, means 90% of them are not diabetic. So if you were to ask me the same question, except this time phrase it, what's the probability that you randomly select 3 people from this population and all 3 of them are not diabetic, it would be 0.9 times 0.9 times 0.9. Okay, I could do that. In fact, I might do that in Excel once I open up a spreadsheet. I'm going to make this a little bit bigger so we can actually see it. Okay, so again, probability, I'm going to find this probability is equal to 0.1 times 0.1 times 0.1. Okay, that's the probability 1 in 1,000, basically, of that happening. But about 0.9 times 0.9 is equal to 0.9 times 0.9 times 0.9. Okay, and that's 73% of the time that will occur. Okay, now there's a kind of funky problem on homework number 2 where it asks you, it tells you, well, let's say that the probability of someone being, I'm going to rephrase this, probably not the same problem, probability of someone being left-handed is, say, 20% in this population, is equal to 0.2. Okay, and you randomly select 3 people from this population, right? You randomly select 3 people from this population. What's the probability that all 3 of those people are going to be left-handed? Well, it's going to be equal to 0.2 times 0.2 times 0.2, okay, which is 0.08. Okay, so so we know that's the way that this is going to behave, right? So you might say to yourself, okay, that's going to, I expect that to happen 8% of the time, right? So what happens now if I instead of having a situation where all 3 outcomes are the same, in other words, I can identify that they're constrained, that the first one has to be heads, the second one has to be heads, the third one has to be heads, or the first one has to be left-handed, and the second and the third have to be left-handed. What if we look at this from the perspective of what would happen in real life? For instance, if we were interested in knowing, well, what's the probability of 2 people from this population being left-handed instead of all 3 being left-handed? Well, there's a lot of ways that could happen, isn't it? So the first person we chose could be left-handed, the second one could be right-handed, the third could be left-handed. But wait a second, something else could happen. The first 2 people could be left-handed, the third person could be right-handed. Well, hang on a second. First one's going to be right-handed, next two could be left-handed. So there's a number of ways to get that outcome. Even more perplexing is the number of ways that there are to get the outcome. Let's say if we were taking a sample size of 10, like if we were to sample 10 people randomly from this population, where 20% of the people are left-handed, and I ask you what's the probability that 3 out of the 10 people are going to be left-handed out of the 10 people. Well, there's many permutations of how that might occur. First 3 people could be left-handed, the first, not 8th and 9th, the first, 5th and 6th, and so on and so forth. It's a lot of ways that can occur. That becomes a very complicated. You could do that literally. You could calculate that using a probability tree, but it would be very cumbersome. Now, I think I might, let me see if I can't find a formula quickly. I don't think I have it handy on Blackboard. Maybe I do. Let me take a quick look. Let's see. Standard normal, binomial distribution problem. Maybe it's in here. Nope, not in there. Okay, let me go back to this. And let me try this way. Use Google, our friend Google. Okay, let's see if I can get this ugly formula to rear its ugly head. Let's take a look at this formula right here. Let me see if I can't get it to look a little bit better for us. Oops, that's not what I wanted to do. Here's a good version of it there. If I can manage to get it to a position where I can drag it off. Okay, I'm going to open this up now. Okay, make it bigger. Okay, let's see what we have here. Okay, let's say that we're interested in the probability that we would get X outcomes given N number of trials. Now, a trial, for instance, when I said let's pick 10 people randomly, each one of those 10 people would be a trial. So the number of trials would be 10, and the probability of success would be the number of people that are left-handed in this case, or the number of people that are diabetic, for instance, in this case. Success being not necessarily a negative or positive thing, negative in terms of diabetic or positive or negative in terms of left-handed, but just meaning that we found a result that we were concerned with. So the probability of getting X number of people out of N number of trials, given the probability of each one, the prevalence of this condition, 20% or so on and so forth. That's determined by this formula, where we have N factorial. N is 10. We know 10 factorial would be 10 times 9 times 8 times 7 times 6 and so on and so forth. And N minus divided by N minus X. Well, let's say I wanted to know the probability of 3 people out of 10, right? X would be our number of successes, and N would be the number of ways that the event can occur, 10, right? So that would be 10 minus 3 would be 7. That's 7 factorial. 7 times 6 times 5 times 4 times 3. And this would be 3 times 2 times 1. And that's multiplied by the probability of P, the probability of successes, which is 0.2, to the X power, which is 3, the number of successes that we're looking for, times Q. Q is 1 minus the probability of success. In other words, instead of 0.2, it's now 0.8. Okay, so this is 0.8 times N, 10 minus 3 is 7. So 0.2 to the 10th power times 0.8 to the 7th power. So to make a long story short, this formula is a real headache to figure out, right? It'll give us the probability of the outcome that we want, the probability that 3 out of 10 people in this population that we randomly select from this population are going to be left-handed. But it's so cumbersome, chances are you would never want to do it. Okay, so we're going to do it in another way. We're going to open up Excel, And you can do this along with me if you want. I'm going to open up Excel. I'm going to get a new table, new window. And make it bigger again. Okay, and I'm going to start with that example, our example of right and left-handedness. Okay, so I want to figure out what's the probability of, that out of 10 people in this population, in other words, the prevalence of left-handedness is equal to 0.2. What's the probability that if I took a sample size of 10, n equals 10, that we would get the number of successes of 3? In other words, 3 out of those 10 people would be left-handed if I randomly sample them from that population. Okay, well, again, I could apply this formula, pretty nasty formula that we saw. That's called the binomial formula. And before I go off any further, by the way, what kind of variable is this handedness? What's that? It's a categorical one, but it's a special categorical one, right? How many values can it have? 2, right? Left-handed or right-handed. Now, Mickey Mantle, of course, was a switch hitter, right? We're not counting switch hitters. We're only counting primary. Actually, tell you the truth, he was primarily a left-handed. Most of his home runs were left-handed. He had like 400 or something like that left-handed, and 150 or so right-handed. But at any rate, so even he was a left-hander, right? So there's only 2 values that this can have. So this is a special kind of categorical variable, right? Left, right. But it's a binomial variable, or they also dichotomous. Binomial, dichotomous, they both refer to 2 values. It can have 2 values. And we run into this a lot. Blood poison, not blood poison, if you want to look at it that way. Premature, not premature. Diabetic, not diabetic. Asthmatic, not asthmatic. So on and so forth. Male, female, and so on. So we work with a lot of dichotomous categorical variables. And this binomial, the nature of the likelihood of counting these things, randomly sampling a population, and then examining the results we have for these binomial variables, they're going to distribute themselves in a special way. And again, it depends on how likely it is to get a particular outcome. Okay, so now I'm going to get back to that in a second, but in the meantime, let's figure out what this probability is. Now, ideally, right now I'm looking at the number of successes, right? And I'm saying to myself, the number of successes I'm interested in right now is 3, right? I'm going to make this. I'm going to center this. Number of successes I'm interested in right now is 3. Okay, and the sample size is 10, and I want to know what's the probability, given that the prevalence is 20%, that 3 out of the 10 people I sample are going to be left-handed. Well, it would be great if there were a binomial function in Excel that would solve this for me, obviously, right? Well, in fact, there is. Equals binom dist. Okay, now you'll notice many of them come up. There's many binom dist, binom inverse. For our purposes for right now, binom dist is plenty for us. When you put in that last parentheses, it comes up and it gives you instructions. Oh, you could also get more detail if you went up here to f of x, as we've discussed before. You can see that it gives us hints as to what it wants as information in order to do this calculation. It wants to know the number of successes, that's going to be 3, comma, the number of trials, which is going to be 20. 20 is the sample size, is the number of trials, times the probability of success. Probability of success is 20% for each individual instance of this. By the way, for one of the rules for binomial distributions is that the likelihood for each random sample is exactly the same. In other words, first time we sample for someone is 20%. Second time we sample is 20%. So it's not going to be changing. And lastly, there's a little thing over there that says cumulative, which we're going to get to in a second. So I'm going to go here and I'm going to say number of successes is 3, comma, the number of trials is 20. The probability of success on any individual selection is going to be 0.2. That's a likelihood of picking a left-hander, comma, and then I'm going to say false for cumulative. It's just going to say false. Take my word for it for the moment. And I'm going to hit enter. As it happens, the probability that 3 out of 10 of these of your sample is going to be, if it's a true random sample, it's going to be about 20.5%, almost 21% of the time you'll get 3 out of 10. Well, why would you want to know this? Well, let's say you're opening a clinic, and you know that the prevalence of HIV in the population, maybe you're giving out free needles or something like that, or clean needles or something like that, needle exchange. And maybe you know in the particular population going to be showing up for your exchange, the probability of being HIV positive is 0.15, right? And you expect to get you expect to get 100 people a day coming to your clinic, and you want to know, well, how many people out of those hundreds, how likely is it that I'm going to get 3 or 4 or 5 or 10 or 12 people that are HIV positive? Because I want enough literature and counseling and so on and so forth that if these people also take an HIV test while they're there, that we have the materials and the counseling and the manpower to counsel them and so on and so forth. So I might be interested how likely it is to have any particular number of successes, given I know the prevalence and given I have an estimate of what my sample size is going to be, right? So it could be important to us. So let's go back to this. So the probability of getting 4 out of 10 people, 3 out of 10 people that are left-handed is about a little over 20%. Okay, well, what about the probability of getting 4 out of 10? What's it going to be? We're going to use the same thing, Binomial Dist, parentheses, and I'm going to do the same thing. I'm going to say number of successes is 3, comma, 10, comma, 0.2, comma, did I do the right thing there? Comma, yeah, 0.2 times, and false. And I'm going to close that. Okay, so the probability of having 4 out of 10 is a little bit lower than it was for, did I do that right? 3, 10, 0.2, false. Yes, I did it right. How about 2 out of 10? Let's try 2 out of 10. Yeah. Did I, and the other one? Did I do that? No, I 3, 10. Okay, that one's right. Oh, you're right. I said a sample size of 20, sample size of 10. Hey, how come you guys at home are not correcting me? I have Brian here. If it wasn't for Brian, who knows what kind of stuff you'd let me get away with? Did I fix it? 10.2. That one's 10.02. False. That looks right. 3, 10. Oh, that should be a 4. There we go. Now we're cooking with gas. Okay, the probability is much lower. It's only 9% that we would get 4 out of 10, right? Because there's only 20% chance of anybody being happen to be diabetic, left-handed. How about 2? Binomial Dist. Parentheses, and now I'm going to do 2, comma, 3, comma, 0.2, comma, false. Oops, I did it again. 2, comma, 10 trials, comma, 0.2, comma, false. Okay, and 1. I'm doing this. It's tedious, but I keep doing this wrong. That's 2. Okay, and see that I got a feeling which outcome you think is most likely. If at 10 people you're going to randomly sample, which outcome is going to be most likely? 1, 2, 3, 4, 5, 6, 7. Probably going to be 2, right? 20% of the population is left-handed. You're going to take 10 people. You figure the most likely outcome is 2 out of 10, 20% of the 10 people, right? You're not always going to get that. In fact, most of the time, 70% of the time, you're going to get something different than 2. But the one result that is going to come up most often is 2. So I'm going to do 1 now. Binomial Dist. Parentheses. I'm going to go 1, comma, 10, comma, 0.2, comma, false. Parentheses. Am I done on the low side? Is there any other outcome on the low side that I could possibly have out of 10 people? 0. Exactly, right. I could have 0 people out of 10. So what's the likelihood of that? Binomial Dist. parentheses, okay, and that's going to be 0, it's successes, out of a trial of 10, out of 10 trials, 0.2, comma, false. And I'm going to close my parentheses, and it comes out to be 10%. It's 10% chance that I would get nobody in that group of 10 that is diabetic. Now, is left-handed, excuse me, I keep mixing my examples up. Okay, so now I'm going to do something interesting here. I'm going to say, what are the other possibilities here? 5, 6, 7, 8, 9, and 10. Right? Those are the other possibilities out of 10. I could have 10 out of 10. Right? Who knows? Notice that as we get further away from the most likely outcome, the probabilities decrease. As you went lower than 2, it decreases. As you go higher than 2, it'll decrease as well. So what is my probability of getting 5? It's going to be equal to binomial dist, parentheses, the number of successes. Well, now what I'm going to do is, instead of going through this whole process piecemeal, I'm going to say the probability of success is 5, but I'm going to click onto the box that contains 5 instead of putting in 5, comma, trials is going to be 10, probability is going to be 0.2, and cumulative is going to be false. Okay, I'm going to hit enter, and now I can drag this down and calculate all the remaining possibilities. So for instance, if I click in here, you can see that it's asking me for the binomial dist for D11, which is 8, comma, 10, comma, 0.2, comma, false, and so on. Okay, so the probability, the most likely outcome, 30% of the time, I'll get 2 out of 10 people. 20% of the time, I'll get 3 out of 10, and so on and so forth. What if I add up all these probabilities? What's the sum of all these probabilities going to equal? This represents all of the possibilities that we might get for this outcome from 10, and it adds up to 1, of course, right? That represents all of the different possibilities. Okay, so now another way I could look at, thank you, Angie, I appreciate that. Now, the other way I could look at this is like, let's say, for instance, I'm interested, what's the probability that I will get 2 or fewer people who are left-handed? In other words, I want to know the probability of satisfying all these 3 probabilities. Could be 2, could be 1, could be 0. What's the probability of all those? Well, all I have to do is take the sum of those possible outcomes, and the probability of getting 2 or fewer is 68% approximately, right? So I could just, and if I want to know what's the probability of getting 3 or more, it's going to be equal to the sum of all these probabilities. That's 3 or more, right? So easy enough to do in Excel. But in fact, we also can do this another way, and this is where that cumulative true or false statement comes in. I'm going to click in here and I'm going to say equals binomial dist, parentheses, and I'm going to say 2 or fewer, eh? So 2 or fewer is going to be, I'm going to say 2, comma, 10 trials, comma, 0.2 is the probability in any individual test, and I'm going to say true this time for cumulative, right? Instead of false. And let me see what I get from that. I get the same thing as if I had added up everything from 2 on down. So if I want to know what the probability of getting 6 or fewer, it's going to be equal to binomial dist, parentheses, and it's going to be equal to, let's see, 6 or fewer is going to be 6, comma, 10 trials, comma, 0.2, comma, and true for cumulative. So everything 6 and below is going to be that problem, is going to include that probability, and it's probably 999 times out of 1,000, or 99.9% of the time, I will get 6 or fewer people who are left-handed. Well, let me throw a little bit of a curve here. What's the probability that I will get 3 or more? Well, I guess I already did that this way, right? I got the sum. What if I wanted to use a binomial dist formula to tell me the probability of getting 3 or more? In other words, all of these probabilities added together, 3 or more. Well, gee, if I use binomial dist, And I'm going to use that true for cumulative. It will only give me a number from that point down. It won't tell me the probability of 3 or more. So what I can do instead is I can say, well, what's the probability of 2 or less? Well, probability of 2 or less, we just calculated, it's this. So if I subtract that from 1, it leaves all the remaining probabilities, which are 3 or more. So I can calculate that by saying it's equal to 1 minus the binomial Dist formula for a 2 or fewer. Okay, and that's my probability, just as we found it there when we did it just by adding up this whole group. Okay, now we can get a little tricky, right? On an exam, I might say something like, what's the probability of getting less than 2 left-handers? Okay, so what do you think the probability of getting less than 2? If I was going to do it here, binomial Dist. Less than 2 I'm interested in. What should I type in there for my number of successes? That's great, Ange. You guys agree with that? 1? If I type in 1, right, comma, 10 trials, comma, 0.2, comma, comma, 0.2, comma, true. Oops, that's a period. Gotta get the right one. True. Close parentheses. That's going to give me the probability of 1 or fewer. Okay, which is the same thing as saying less than 2. If I would ask you what's the probability of getting more than 5, right? More than 5. Well, more than 5 does not include 5. So in that case, I would say binomial Dist more than 5. Okay, what would I do there? I would say 5, comma, 10, comma, 0.2, comma, true, and that would give me the probability for everything 5 and less. So the probability of more than 5 would be 1 minus that. It's going to be equal to 1 minus that, because that's what would be left after I subtract that from this some of these probabilities. If I subtract it from 1, it would be 6 or more. Okay, or more than 5. Another way of saying that, it's more than 5. Okay, so that's pretty interesting, right? I mean, this gives us an idea of how things might shake out if we were to take a sample like this. I'm gonna repeat this for just one more time. I'm gonna do it very quickly. I'm gonna go over here. I'm just gonna copy this, and I'll paste it over here. And I'm going to say equals binomial Dist parentheses. I'm going to take 0, comma. I'm going to say the number of trials is 1,000, comma, and the number of successes is 0, because number of trials, and the probability is 0.5, comma, like a coin toss, comma, and I'm going to say false. I want each individual probability. I'm going to hit enter. So now that's very in 1,000 to get 0. You can flip 1,000 coins. If you're going to flip 1,000 coins, probability of getting 0 out of that 1,000 is very small. Okay, and I could go and drag this up. Right, and I could find all of these. These are all going to be very small numbers. What's going to be the most likely for 1,000? A sample size of 1,000. What's going to be the most likely outcome for when I flip 100, when I flip 1,000 coins? What's going to be the most likely outcome? Most likely outcome is going to be 500 heads and 500 tails, because 50-50 chance. That's not going to happen most of the time. Just like here, most likely outcome was 20% of the time, but it didn't happen. Or it didn't happen exclusively. There are a lot of other possibilities. But what I did notice was that based on chance alone, that as I got below that, further and further and further from the most likely outcome, look at that as kind of a mean, the most likely outcome, as I got further and further from that, the less likely that outcome would be. So in other words, I wound up with a distribution that was had a lot of frequency in the middle, and fewer outcomes that came out that way as you got further and further away from the most likely outcome. That's our bell-shaped curve that we started to talk about. That's our normal distribution. In this case, it's called a Poisson or a binomial distribution, but it's the same idea. I'm going to show you a quick video. I'm hoping that if you can't see this online, okay, you can play it for yourself in another window. But this is an example of a machine. It's called a Galton machine. Okay, and what the machine does is it demonstrates the binomial probability. Remember, there's two possibilities: heads, tails, left, right, left-handed, right-handed, and so on and so forth. In this one, each outcome has a 50% chance. And in this one, the outcomes could be left or right, kind of like left-handed, right-handed, except that there's an even chance of both, right? So 50% is the outcome. So let's take a look at what's going to happen here. Let me see if I can't blow this up.
0.04,
Okay.
comma, except this time I'm going to say true.
Okay.
Right, and this.
Now notice I went through this whole nasty thing here. Again, this is from another session. You can. I'm going to be putting this up. The version of this that we went through. This version is a little bit different, but I'm going to show you a version of. You can look. I'm leaving this up here so that if you want to go through a second version of it, you have it there. But it's from a previous recording, so you don't have to go through this whole thing. But I want to get to the part where you can see the Galton machine. I don't see it there. So I'm going to, instead of doing that, I'll leave that to your devices. Let's see if I can't find the Galton machine on here. Okay. Oh, first of all, what is a Galton machine? Okay, Galton machine, let me show you a little drawing. Okay, here's an example of a Galton machine. What happens with a Galton machine is that we take a bunch of ball bearings or marbles, we drop them in the top, and these slide down from the top. This stands vertically. Yeah, you ever seen a pachinko machine? You guys, anybody online know what a pachinko machine is? It's kind of a Japanese pinball machine. It stands vertically. You get a chance when you get a chance. Google pachinko, P-A-C-I-N-C-K-O, I think it is. Okay, it's kind of a Japanese pinball machine. Pachinko, that's right, right? So this is kind of like almost like a pachinko machine, but it's special purpose. And the way this works is that this ball, this round marble or ball bearing, is going to drop straight down through this funnel, and it's going to hit a pin. When it hits that pin's in the dead center. Sometimes it'll go to the left, and sometimes it'll go to the right. Which direction it goes to is chance. Could go either way. And then once it bounces off of that, it encounters another pin. And that pin, it could go to the left or the right, and left and the right, and so on and so forth. And it can bounce down here going left, right, left, right, left, right, left, right. If you get an even number of lefts than rights, it's going to come out and go into the middle column here, or middle tube when it collects at the bottom. So an even number of lefts and rights, which is a likely probably the most likely outcome, is going to fill this middle tube. But then if you get more lefts than rights, it's going to go this direction instead and maybe fall into one of these tubes. If it does nothing but make lefts, it's going to go into this last tube. And we know from probability that if it's a 50-50 chance left, right, if it's going to go through 20 rows of these pins, it's not very likely it's going to wind up or make all left turns and wind up in this tube, or make all right turns and wind up in this tube. So the way that they collect in here is going to represent the binomial distribution, the probability given a 50-50 chance of one outcome or the other for a dichotomous variable. What is the probability that you would get an outcome that would represent 11 left turns and 12 right, or 10 left turns and 12 right, and so on and so forth? What's the probability that each would occur? And you'll see that the further away you get from exactly even number for a 50% probability, right, same number in either direction, the less likely that outcome becomes. And someone actually built this machine to demonstrate this. I'm gonna play it for you. This machine is actually located at the New York Hall for Science, which is in Queens. It used to be the Queens Museum. I think it was part of the World's Fair in 1964, and they kept it going and they turned it into a science museum. It's got rocket boosters there. It's got a million different activities for kids. in optics and math and space science and stuff like that. So if you have any kids, in about 10 years, you'll be over there, playing with that stuff. Try not to touch anything because they're really gooey, these kids, and they carry all sorts of germs. So wear gloves while you're there. But at any rate, there's a million kids there, and they're really all enjoying themselves. I may not be able to run. I may have to dig up a different version of this. Okay, so let me see if it'll work. I may have to do a conversion. Okay, here we go.
This odd-looking device is called the Galton machine, or Queen Cups. It's located at the New York Hall of Science in Queens. As balls drop in from the top, they strike pins that are located in their can. They have an equal probability of going to the left or the right of each pin. Watch as these balls follow the seemingly random paths down to bins at the bottom of the device. In the bins, we see a definite pattern taking place. Today, we're going to examine how such a seemingly random series of events could produce such a predictable outcome.
Right? So you saw that. That's a binomial distribution. That's a form of a normal distribution. Were you guys online able to see that if I played it on here? Good. Okay. You also have it. You have the link also if you want to see it on the link. I'm glad you were able to see it. But this is real life. This is the way real life distributes itself. A lot of the things that we're going to be learning about as we move forward are things that show a normal distribution, things that show a patterns that are due to chance. And once we understand how chance affects selection, in other words, when we take a sample from a population, how chance affects the results of our sample compared to what's in the population. Once we start to understand that, then we're going to be able to make all sorts of predictions about differences in populations, comparisons of two groups, probability of being right or wrong about making a distinction, and so on and so forth. It's going to become very valuable to us. Okay, so I'm going to move on to the next file that I have here. Okay, and that's called Binomial Distribution Empirical Rule. Well, that's the way a binomial distribution would distribute itself. And that's the way we might do calculations or run into problems that involve a binomial distribution. So I'm going to open Microsoft Word and open this document that we have. It's from a few years. This is a few years old, but it's the same thing. Nothing's changed. Okay, many physical traits you'll find, or things involving chance, or things involving measurements, biological measurements, and so on and so forth, are distributed approximately normally. And what do we mean by normally? It means that they're distributed in a kind of a bell-shaped curve. Most of the results are in the middle. So for instance, if I'm looking at a distribution of weights, the average weight for all Hunter students, all Hunter nutrition students, and the middle is going to middle of this distribution is going to be the average or the median. Okay, and in true normal distribution, we have a few characteristics. The mean and the median are the same; they're the same number because the distribution is symmetrical. In other words, the left is a mirror image of the right part of this distribution. So they're symmetrical. Not only are they symmetrical and the mean and the median are equal, but they show certain distribution patterns that as you get, in other words, if the average weight of students in Hunter is 130 pounds, right? The average, right? That as you get further and further away from that weight, you'll find fewer and fewer students. There won't be as many students that are 120 or as many that are 110. And there'll be even fewer that are 100 pounds. And there'll be very few that are 90 pounds. And there'll be very few, even fewer, maybe none that are 80 pounds. Similarly, as you get higher and further away from the mean weight, you're going to get fewer and fewer people that represent that mean weight. The height of this curve represents the proportion of the population, or your sample for that matter, proportion of the population that is represented by that particular area, that particular weight. Okay, so in other words, we're looking at the mean. In this particular case, it looks like about 40% of the population, somewhere around the mean. In fact, we can actually divide this up, except that Since these normal distributions all have the same kind of properties, same mathematical properties, we can even go further than that. And this is something called the normal distribution's empirical rule. Okay, and the way that this works in a standard normal distribution, a true normal distribution, we don't expect them always to be perfect, but in most normal distributions, then pretty much 68% of the people, the sample, the results lie between one standard deviation below the mean and one standard deviation above the mean. Okay. Notice I didn't say a number, right? So the interesting thing about this is, let's say I told you that I sampled my population. I know I got a very big sample, and I'm pretty confident that the mean is 120 and the standard deviation is 10 pounds, right? Well, then I could have told you that, oh, well, the mean is 120 and 68% of the students are between 110 and 130. I could have told you that, but that would only apply to that one distribution. But by looking at it this way, in terms of the arithmetic mean and in terms of the number of standard deviations below or above the mean, we can now apply this to all normal distributions going forward. So 68% of the population is between one standard deviation below and one standard deviation above. 95% of the population is between two standard deviations below and two standard deviations above. You can see that up here. And 99.7% of the population is between three standard deviations below and three above. So in our example I just gave you, 120 plus 3 times 10 would be 150, and minus 30 would be 90. So 99.7% of the population of this particular population would be between 90 and 150. Okay, but we usually like to view this in terms of standard deviation and mean, because then we can apply this to a lot more stuff. Let's give this a try now. Okay, and this is going to be very powerful. It's going to tell us a lot of interesting stuff that's going to be very important to us. Okay, so let's take a look at this first example. Assume that the heights of adult Caucasian men has a mean of 68 inches. Okay, I'll highlight that. And a standard deviation of 4 inches. Find the probability that a randomly chosen individual from that population has a height greater than 68 inches. I'm going to go back up here and take a look at this. Okay, now keep in mind, this can represent any normal distribution. Okay, so our mean is here, right? In this case, our mean is 68 inches, and our standard deviation is 4 inches. So this would be 4 inches and 4 inches and 4 inches away from the mean, and also below the mean. What's the probability? Now remember that this is a probability distribution, right? In other words, because it's normally distributed, and this mean the average is in the middle, we know that half of the people are under the mean, the average, and half of the people are above the average. So that should help you out with that particular question. What's the probability that a randomly chosen individual from this population has a height greater than 68 inches? Anybody want to attempt that online? Yeah, 50%, exactly, right? So it's 50% of if you took a random sample from this population, you'd have 50% of the time you would find that they were in the upper half of this population. What's the probability that if you randomly selected someone from this population, that their height would be between 64 and 72 inches? 68%. Right, you're right, exactly. How about you guys online? What do you guys think? Hang on a second. Angie had a good idea there, but not quite. How many standard deviations below the mean is 64 inches? It's only one, right? And 72 is one above. So it's going to be one standard deviation into one standard. So it's going to be 68. Okay, when you get to the next one, 60 and 76, you beat us. Ange beat us to the right answer. She just got there ahead of us, right? This last one, 60 and 76, is 2 standard deviations below and 2 standard deviations above. So that's going to be our 95%. Okay, so let's try the next one. Assume that the heights of adult Caucasian women have a mean of 63 inches and a standard deviation of 3 inches. What percentage of women in this population have a mean height greater than 63 inches? That's an easy one, right? Bingo. How about greater than 66 inches? There's a little bit of a curve there, right? What about 66 inches? Right? So the mean is 63 inches. Standard deviation is 3. So we're standard, and we want to know what percentage is above one standard deviation. Okay, anybody want to hazard a guess on that online? Well, if we got 68% here, right, in the middle, right, then we have 32% left between the lower half of the distribution and the upper half of the distribution. So 68%, 32, 16% here, 16% here. So approximately 16% of the population is above 63 inches, 66 inches, one standard deviation above the mean. Okay, I'll get you guys to answer this. What percentage of population would we expect to be less than 60 inches? 63 inches, less than 60, right? Less than 60. Let me see a guess online. You jumped ahead, didn't you? Right, the mean. What was the mean? 63. The mean was 63, and I'm asking you what percentage is less than 60, right? So less than 60 is 16ish, right? Exactly, about 16% of the population. But you had the right idea. If I had said no, actually, you didn't jump ahead of me. You got the right answer, right? You got the right answer. I thought you. Let me give you another one before we move on to the next one, which is probably going to appear there anyway. What's the probability that we would randomly select someone whose height is less than 57 inches? Well, actually, not quite. Right? Remember, 95% of the population is between 2 standard deviations above and 2 below, right? So that's going to leave 5%, 2.5% in the bottom, 2.5% in the top, right? You have to remember that's not the middle 95%. So we would expect about 2.5% of the population to be less than 2 standard deviations, more than 2 standard deviations below the mean. Okay. Similarly, if I asked you what's the probability of randomly selecting someone that is what was it? 63 plus 6 is going to be 63 plus 6 is 69 inches, right? Taller than 69 inches, it would be 2.5%, except on this end as opposed to on the lower end. Okay, that part a little bit more complicated, but you get the idea. Okay, let's try the next one. Okay, except next one, I'm going to try something a little bit different. I'm actually going to take a piece of paper and I'm going to draw it. Assume that the heights of adult Caucasian women is that same problem. No. This isn't. Yeah, that's the same problem. The gestation time for humans. There's just one for you. The gestation time for humans has a mean of 266 days and a standard deviation of 25 days. What percentage of pregnancies would you expect to be greater than 291 days? Well, I'm going to do something a little bit different here. And what I'm going to do is I'm going to open up a blank piece of paper for me to work with. I'm going to save that. And yep. So this time, I'm going to take this blank piece of paper, and if things work out right, I'm going to be able to write on it. Okay, so what was this? 266 with a standard deviation of 25. So I'm going to take this, I'm going to sketch my own standard normal distribution. Okay, so whoops, I need to leave that turned on. Okay, so here is my normal distribution. Not beautifully drawn, but it'll do for our purposes. So the mean is, what did I say, was 266, right, is mu. And our standard deviation, sigma for the population, is 25. Okay, and I'm asking you, what's the probability that we'd randomly select someone that it's greater than 291 days, a pregnancy greater than 291 days? So I'm going to stick it over here somewhere, 291 days, right? Well, how many standard deviations above 266 is 291? Yeah, it looks like it, right? So how would I figure that out? I would say 291 minus 266 is equal to 25. So it's one standard deviation above the mean. So I know that 68% of the outcomes are going to be between one standard deviation below and one above. So the probability that's left up here is going to be half of the 32% that we didn't account for, which is going to be about 16%. Okay, so how about less than 241 days? Well, 206 by 241 is minus 20, it's minus 25, right? So it's one standard deviation below the mean, right? Which would mean the probability of getting a value less than this is going to be about 16% also. Oops. 16% also, right? Okay, how about the probability of less than 241 days or greater than 291 days? Right, that's gonna mean that we have both possibilities, right? So the probability that we would get a value that's less than a probability that's less than 241 and greater than 291 is going to be 16% plus 16%, right? What's the probability we would get a value that's greater, that's less than, that's greater than 247, oh, 241, excuse me, and less than 291, right? It's going to be between 241 and 291, right? That's going to be our 68%, isn't it? Right? It's going to be between 241 and 291. Okay, let's move on from that. Okay, so now that's very nice. This is very gratifying if we get into a situation where we're only dealing with questions that involve the value, the exact value coming out to exactly a whole number of standard deviations above or below the mean. Unfortunately, that's not going to be the case most of the time, right? There's going to be other things that we're going to be interested in evaluating. Okay, so let's take a look at where this might go. This first one I think is going to stick with our usual outcomes here. Assume that the average heights of U.S. women have 63 inches, standard deviation this time of 2 inches. What percent of women would you expect to have a mean height less than 63? Well, the mean is 63, so we would say 50% there. Less than 62 inches. Uh-oh, we have a problem now, don't we? Right, so what is that problem? So I'm going to sketch my normal distribution again. Okay, so here's my normal distribution. And my mean was, what did I say, was 63 inches? Right, that's my mean. That's mu. And my standard deviation is equal to 2. And I want to know what's the probability of having, selecting a woman that has a height less than 62 inches. Now that's going to be over here somewhere. Right, well, how many standard deviations below the mean is 2, is 62 inches? Yeah, that's only half. We're going to introduce a new concept here. We're going to introduce something called a z-score, right? And z is going to represent the number of standard deviations away from the mean. Okay, and I'm going to actually turn this into a formula to make it so that we don't have to think too hard when we're calculating this, right? I mean, this is simple enough. It's just a half. We're going to say z is equal to the value we're interested in, x, minus the mean over the standard deviation, right? So in this case, z is equal to 62 minus the mean, which is 63, divided by the standard deviation, which is 2, is equal to 1/2. Not just equal to 1/2, what else is it equal to? Yeah, negative. What does that negative indicate to you? Right, exactly. It's below the mean. It indicates that z-score means that it's below the mean. Okay, so how are we going to figure this out? Well, we don't really have the empirical rule. Is only number one. It's only number one an estimate, right? And number two, not only is only an estimate, but it only works for whole numbers, right? Well, it doesn't give us very much information otherwise. Helps us bracket stuff, but really doesn't give us any solid numbers. So I am going to need a way to calculate the areas that are represented here, because those areas that are represented here, like the area below 62, that represents the probability of, that represents a couple, you can look at it a couple of ways. One is that could represent the percentage of women that have a height below 62 inches. You could look at it as saying the number of women in this population, total population, have a height below 62 inches. Or you could look at it as the probability of selecting a woman randomly from this population and having them be in this area below 62. So you can look at it a few different ways. Any one of those is correct enough. Okay, so we need to know a way to calculate this area below 62, since that's what the problem is asking us. What's the probability of, what percentage of women would you expect to have a mean below 62 inches, okay, in this population? Okay, so we need a way to look this up. Okay, well, fortunately on Blackboard, we have, and in your textbook and so on and so forth, we have a table you can use to do this. And I'm going to go to that table right now if I can find it. Okay, here we go. So I'm going to go to the Z table. Okay, this table represents the areas that are indicated by different z-scores. So for instance, if I see a z-score is 0, that represents 50%, because half the mean is above that point, half of the distribution is below that point, half of it is above that point. That represents the mean. The mean has a z-score of 0. As you get further away from the mean, the z-scores, this is the number of standard deviations, right? -1 standard deviation is about 16%. Remember that we just were playing with that. +1 standard deviation is about 84%. Well, that's weird. We said 16% before, right? The reason why we got 84% for that 1 standard deviation above the mean here is because the way that this table works is if you identify the z-score, it will tell you the area to the left of that z-score. So when we're looking at a z-score of -1, it's going to tell us that that area is about 16%, right? But if we're looking at a z-score of +1, we're going to use this other chart here for positive number z-scores. That z-score indicates that the area is going to be equal to 84%, leaving 16% above. It's always going to give you the percentage to the left, not to the right. And all you have to do to calculate the area to the right is subtract the area to the left from 1. Right? So that should be easy enough for us to do. So in this case, the question was, in this case, what's the probability, or what percentage of women in this population have a height less than 62 inches, which turns out to be a z-score of -0.5. So let's look at the negative z-scores. It's going to be this table, right? And we already know it's going to be less than 50% because it's going to be below the mean. So I'm going to look for -0.05. Here we go, -0.05. But notice there's a lot of numbers here, right? And what happens here is that very frequently we're not going to have a single decimal place for a z-score. We might have a z-score of -0.52, -0.59, and so on and so forth. If you look at the way this table is laid out, this represents the first 2 digits of the z-score. In our case, -0.5. And the second decimal place is represented by the column. So this would be 0, the third digit 0, third digit 0, third digit 0.1, 0.2, 0.3, 0.4, and so on. Okay, so essentially, if we wanted to know the area represented by -0.5, we would just take this first one because it represents -0.50, right? If we were interested in the area represented to the left of -0.55, we would say, well, this is -0.55, 0, 1, 2, 3, 4, 5. This would represent z-score of -0.55 or 0.56 or -0.57 and so on. So what area are we talking about in this particular issue? It's 30.85, right? 30.85. That's the percentage of people in this population, or the probability of selecting someone from this population below half a z-score below the mean. Okay, so I can go back to here.
Yeah, but that's 62 inches or less. It says less than 62 inches.
Well, actually, Actually, you don't have to worry about that, because technically, when you look at this normal distribution, right, 62 is a vertical line. A line has no area, right? So in other words, the idea of 62 or less than 62 is really the same thing, because the line itself doesn't take up any space in this distribution, right? So the height here is meaningless to you. In other words, this height could represent, in other words, this really represents a probability of that outcome, with the most likely being the mean, which is why it's high at the highest in the middle. But the fact is that any specific outcome is basically represents a straight line, which is no area at all. It's no area at all. So you don't have to worry about whether it's 62 or less, or 60 or less than 62. In the binomial distribution, you can, because each solution is discrete. There is a real quantity or probability associated with 4 out of 10 versus 3 out of 10. In this case, you're really just looking at the probability for the whole population, so you don't have to worry about that here. But that's a good point. So that's how we would solve that. Now let's give the next one a try here. Okay, the next one says, what's the probability of a woman have a height greater than 66 inches for this same distribution? Okay, I'm going to pick up my pen and I'm going to give this a try. Greater than, what did I say, 66? Okay, greater than 66 inches. Okay, how many standard deviations away from 63 is 66? We're going to do that. C is equal to, well, it's actually calculated as equal to X, which is 66, minus 63 over 2 is going to be equal to 1.5, right? Or 1.50 if you wanted to put that there. Okay, so we're in the area that's greater than 66 inches, right? So we got z-score. Notice what's the sign on this? It's positive, because it's above the mean rather than below the mean. And if you just work out the numbers correctly, it'll always give you the right sign anyway, right? So it's a positive 1.5, but we're looking at this area here. So the z-score is going to be 1.5. So let's go back to our z-table. If I can find it again. The only problem with using a small screen laptop. Okay, positive 1.5. 1.50, that's going to represent an area of 93.32%. So I'm going to go back here. 93.32%, or in other words, 0.9332, right? Well, what area is that going to represent? That's going to represent the area to the left of that value 66, or a z-score, or which is also represents a z-score of plus 1.5, right, to the left. But we're not interested in that area. We're interested in this area. How do I find that area? Well, I take 1 minus 0.9332. Okay, and that's going to be 0.06. I'm gonna see 68. Does that sound right? Something like that. Something around 6 or 7%, but a little less than 7% of the population is going to be above 66 inches. Or you could also look at it from the perspective that the probability of selecting a random individual from this population who's greater than 66 inches tall is approximately 7 inches. Oh, I got to kill my messages here. Let's see what I have to do that. Okay. Hopefully this stuff goes away. Okay, so anyway, that's where we stand. Okay, so now let's take a look at the next question here. I wanted you to notice something. I've been doing this for 1,000 years, right? I'm like a relic. I've been doing this forever. Notice that I actually sketched this out using a normal distribution. Okay, by all means, rather than do this in your head in the beginning, sketch this stuff out so you can get a feel for what you're doing here, because these are relatively simple examples that we're trying here. As we continue, these examples are going to get harder and harder. Okay, and real life versions of this are going to get harder yet. So let's go to the next one. I'm going to have you guys do this. I'm going to give you guys 10 minutes to do this problem. Okay, the body temperature of adults has a mean of 98.6 degrees Fahrenheit and a standard deviation of 0.6 degrees Fahrenheit. Find the probability that a randomly selected individual has a mean body temperature A greater than 99 degrees, B less than 98 degrees, C less than or greater than 98 or less than 98 or greater than 99, and between 98 and 99. Okay, so I'm going to give you guys 10 minutes to work on that yourselves. And we'll come back and we'll go through this together. Okay, good. I'm going to get to this right now. All right, let me get to a blank piece of paper again so we can work this out together. And okay, so since you've done this, I'm gonna sketch this. Since you guys have done this already, whoops, let's put that down. Here's my normal distribution. My mean is 98.6, and I'm interested in 99 degrees. And I'll throw this over here, 99 degrees. I'm interested in 98 degrees. Oops. 98 degrees. And first of all, I'm interested in what percentage of these, if we pick randomly select an individual, what's the likelihood they have a mean body temperature that's greater than 99 degrees? In other words, greater than 99 degrees. Our standard deviation was 0.6 degrees. Okay, so let's see what we're going to have to do here. So I'm always going to use the formula just to make sure I get things straight, so my signs are straight and so on and so forth. So I'm interested, my formula is x minus mu over the standard deviation. Difference between the value I'm interested in, the mean, over the standard deviation is always going to give me the number of standard deviations away from the mean. So it's going to be equal to, in this case, 99 minus 98.6 divided by 0.6 is equal to 0.4, positive 0.4, over 0.6 is equal to 2/3. It's equal to 0.667, for instance, or 0.67. Most likely is the way we're going to be using in our case, because I'm going to go to the table. Okay, so that's my z-score. I want to know what area this represents above it. I know my table is only going to give me the area below that. Okay, so let's see what I get. Okay, I'm going to go to my table here. So a positive z-score of 0.067, 0.60, 1, 2, 3, 4, 5, 6, 7 represents an area of 0.7486. So 0.7486 to the left of 99. But I'm interested in the area to the right of 99, so it's going to be 1 minus 0.7486. So I'm going to say that that is going to be equal to, I'll do my quick calculation here, 1 minus 0.7486, and that's going to be equal to about 25.14%, 0.2514. Right, so this area is 0.2514. What does that mean? That means that 25% of the population has a temperature above 99 degrees. It means the probability of me selecting an individual, measuring their temperature, that the probability that an individual will have a temperature above 99 degrees is 25%, etc., etc. Now, of course, your thinking, as all students think, well, how much should I round this? And the answer to that question really, depends on all sorts of interesting things like significant digits and how precisely you know the information, how many digits I gave you the mean and the standard deviation, a million other things. But for our purposes, as you're doing calculations, don't round until the very end. Okay, you guys are using calculators, Excel, so you really don't have to round yet, right? For our purposes, usually, in most cases, I'll give you some guidance. I would say in this particular example, I might say, I know this to three significant digits, 9, 8, 6. There's three significant digits there. So maybe I'll round this as three significant digits, so 0.251, or in other words, 25.1%. So I might use that logic in rounding. I don't round until the very last step, though. The reason why I do that is because in some cases, some of the calculations that we're going to do in the future are going to involve squaring values or finding the square root of values, right? And what happens then is that if I take a number like 2.1, right, and 2.134, and I round it off to 2.1, and then I square it, when I square that number, I multiply the error in squaring it. So I don't want to round it until I've gotten to my very last calculation and completed it and got my answer and just fill that answer in. Okay, so long story short, don't round until the very end. And when you do round, look at the significant, either look for any guidance I've given you if it's a homework or an assignment, or look for the number of significant digits that you're giving the information in. 98.6 degrees. Well, maybe I'll keep using three digits, like 0.251, and so on. So that's what the approach I would take to it for now. Okay, how many of you guys got that right? Did all of you guys get that one right? No? Oh, what was the problem? I'm more interested in no than yes. What was the problem on the no? What was the issue there? Do you know what the problem was? Is the important thing. Okay. Oh, good. Okay, good. Excellent. So let's take the next part of this. How'd you do on that? You got that right? What's that? What was the issue there? What?
I used the 0.67 and I used that as the z-score instead of going to get the z-score.
Okay, good. You got to go to 10. That's the number standard deviation. Now you got to turn that into an area. Right, exactly right. Okay, what about less than 98 degrees? Actually, that's more direct, isn't it? So if I go 98, right, I'm going to take x minus mu, which is 98 minus 98.6 over zero point 0.6, our standard deviation, and that's going to be equal to minus, notice it automatically works out the minus sign for you, minus 1 standard deviation below the mean is 98 degrees. So I'm going to go over to our table, and you could use the empirical rule here because it's an even number, it's a digit, it's an integer, but you'll find that it's actually more accurate in the table than it is. Remember, that's only an estimate, that empirical rule. So -1, remember, you don't want to use positive 1 because it's gonna be all the way over here. 98 is down here to the left of the mean. So negative 1.00 is 15.87, 0.1587. So this area is 0.1587. And that is actually the area that we're looking for, isn't it? Right? It asks us what's the probability of someone having a temperature less than that value. Well, how about the combined possibility of having a temperature less than 98 or greater than 99? Well, either one of these meets that criteria, so we would add these two together. We would add 0.2514 and 0.1587, add them together, and we get 0, carry 1, 1. We'd get 41, about 41%, 0.410 is the probability that we would pick an individual, a random individual, and they would have a temperature either higher than 99 or 99 or lower than 98. Right? Either one of those two possibilities. Okay, and finally, what's the probability of having a temperature between 98 and 99? Well, we know that this area is 0.1587. This area is 0.2518. Combined, they represent 41% of this distribution. So that means we're left with 1 minus that, or I'm not going to bother calculating exactly, or about 59%. Oops. Or about 59% of the population, or 59%, the odds of picking someone and find unit temperatures between 98 degrees and 99 degrees. That'll occur 59% of the time. Okay, are you guys okay with that? Can I move on from that? No, you're not okay, and I can't move on from that. Okay. All right. Let me see. Let me see what else we have here. Okay. I'm going to do another example or two. Let's see if it sinks in a little bit better. Another example or two. Remember, because we're recording these sessions, you can always go back and, plow through them again, do the examples again. Okay. And also I've put some videos from previous semesters on. So perhaps, I kind of maybe I communicated it a little bit. There's also occasionally you'll see a lecture by another professor that I've recorded that I've included here as well. Okay, so now and remember, you don't have to worry about viewing those or being responsible for them because they're meant as supplemental materials. You can just stick with the classroom materials and the textbook and the assignments and the exercises that we do in class and so on and so forth. But if it's on occasion, it's good to hear that's presented in another voice, right? So you have those that you can take a look at as well. Okay, so percentage of elementary school teachers. Elementary school teachers in the United States have a mean salary of $32,000 and a standard deviation of $3,000. Find a percentage of teachers that you would expect to have a salary greater than $36,500 or less than $28,000. That should be $28,000. I think these are. I think these are examples I usually don't get to, so they'll go a funkier. The next one's going to be an interesting one. So let's do this one. Let's get past this one, and then we're going to take the next one, which might be a little bit more interesting. I'm going to close this, and we can do this together. I'm not going to go offline to do this. Okay, let me get this out of the way. Okay, and I think I said that my average salary is $36,000. 32,000, thank you. 32,000 and my standard deviation is equal to $3,000. Okay, and from that point, I'm going to solve this problem. And the problem was assume that find the percentage of teachers you would expect to have a salary greater than 36,500 or less than 28,000. So we're looking for, whoops. Did I do this the wrong way? There we go. Greater than 36,500. Or less than 28,000. So greater than this or less than this. I'm going to do this backwards. I'm going to start with the 28,000 first. Okay, first thing I have to do is find the z value for that 28,000. That's going to be 28,000 minus the mean 32,000 over the standard deviation, which is 3,000. Okay, so that's going to be 4,000 over 3,000. Okay, actually it's minus, so it's going to be equal to minus 1.33. And I notice I rounded to the third decimal place because I know I'm going to be using the z table, and I know I can't, on our particular z table, I won't get any more precise than that anyway. And on the upper side, I'm going to calculate my z-score now also, is equal to 36,500 minus 32,000 over 3,000. So that's going to be equal to, it looks like, let's see, 4,500 over 3,000 is going to be equal to 1.5. And that's going to be a positive 1.5, right? It's going to be negative 1.33 because it's below the mean. It's going to be a positive 1.5 because it's above. Let's start with 28,000. Okay, here's our negative 1.33, 1.3012 3, that represents 0.0918. That's the proportion that we're looking at there. This is 0.09, what was it again? 18. Or in other words, 9.18%. Okay, 9.18% of the population is going to have a salary less than 28,000, assuming that it's truly normally distributed. Or again, if I randomly selected a teacher from this population, there's a 9.18% chance, or a 0.0918 proportion, that would have a salary less than that. Okay, this 36,500 above that can be a little bit trickier, right? Because again, we want the area above it, so our Z table only gives us the area below, so we're going to have to subtract from 1. So I'm going to go to our Z table, and that was 1.5 plus 1.50, and that area represents 0.9332. So the area to the left of this 36,000 is 0.9332. So the area to the right is going to be 0.0768, I believe. Okay, that should work. About 7.5, a little more than 7.5%. Right. So about 7.5% of these teachers are making more than 36.5. About 9% of them are making less than 28,000. Sounds like those. Where were those teachers that went on strike? Was that Oklahoma or something like that? It's one of those square states out west, right? Anybody remember what state that was? There's actually been 2 or 3 of them, but one of them was, the salaries were particularly low. I think it was Wyoming or Oklahoma or something like that. As a shortcut, could you use whatever the area is for the complementary negative z-score? Let me think about that for a second. Yeah, that sounds right. Yes, because they're symmetrical. The Carolinas, okay. I think that's right. If you're looking for the area, yeah, because basically what you're doing is you're saying that, well, if the z-score is this and you got to subtract 1, if I take the z-score here, because it's symmetrical, and if I take the z-score for negative 1.5, that area that's below that is going to be the same size as the area above a z-score of 1.5. And that's true because they're symmetrical, right? Excellent. That's a good point. Excellent point. Okay. So I'm going to move on to something a little bit different. Okay, assume that blood pressure readings have a mean of 120 and a standard deviation of 8. What blood pressure would you have to exceed in order to be in the highest 10% of this population? Whoa, that's a real curveball there, right? Let me draw this. Let me get a fresh piece of paper here and draw this. Let me reread that. So we're looking at a mean of 120 and a standard deviation of 8. Mean blood pressure is 120 and the standard deviation is 8. And we're interested in knowing what your blood pressure has to be in the top 10% of this population. So we know the area is 10%, but we don't know what the value is we don't know what blood pressure that represents. This is the inverse, or the converse rather, more appropriately, of what we've been doing up to now. We know the area, but we don't know the value. Well, in fact, we can't get to the value directly. We can figure out what the z-score is first. In other words, what z-score represents an area in the top here of 10%? Well, that z-score already represents an area to the bottom of 90%. Right? This is whatever this z-score is, it represents a value, a z-score, which would have 90% to the left of it. Okay, so I'm going to go on here, and I'm going to go to the table. And let's see. I'm going to go to Z table, and I'm going to look for the area that represents 90%. the area that's closest to 90%. So let me see, 89, 88, 89.44, 89.62, 89. So this looks like the closest to 90%. So what z-score is that? That z-score is 1.28. 1.28. So the z-score that represents 10% of the area left, or 90% below, above 10% above 90% below, is 1.28. So I've used this table backwards. I found the area by looking in the table itself and then reference what z-score that represents. Okay, so the z-score for the point at which 10% of the population has blood pressure above that level, the z-score is 1.28. But I'm not really interested in the z-score. I'm really interested in what blood pressure is that. Well, I'm going to bring back a formula we used before. Z is equal to x minus mu over sigma. And whenever you solve these kinds of problems, you're always looking at a form. When you look at a formula, you're always looking to get down to one unknown. Because if you get to one unknown, you can solve the problem. We know what mu is. We know what sigma is. We know what z is now. The z that we need now for x to be. The only thing we don't know is x. So I'm just going to plug these in. 1.28, right? It's positive because it's to the right of the mean, is equal to x minus 120 over 8, right? And I can cross multiply, right? This is over 1. I can cross multiply. X minus 120 is equal to 8 times 1.28, right? So X is equal to 120. I'll move it to the other side, becomes positive, plus 8 times 1.28. Okay, and so let me see what that is. 8 times 1.28. Right, is equal to 10.24 plus 120 is equal to 130.24. So X works out to 130.24. Okay, so the z-score of 1.28 represents a value of 130.24. So if you have a blood pressure above 130.24, you're in the top 10% of this population in blood pressure. Okay, did that totally lose you guys? Okay, you guys comfortable with that? Most of you guys think you got that? You see how we turned it around there? And we used the area to determine what the z-score was. Are you okay with that, Brian?
We'll take some practice.
Okay, good. Good. Practice is always good, right? Exactly. Okay, good. Excellent. Okay. Okay, let me see if I want to get into this. Okay, actually now, I think now's a good time maybe. Let's take a break for 10 minutes. Okay, go have a cocktail if you're online, have coffee if you're here, use the bathroom, whatever, right? And let's take a break for 10 minutes, come back at 7:30 or so, approximately 7:30, and we'll pick up where we left off, except now we're going to move over to Excel and see how these functions are all buried in Excel also. So we have access to them tables, we have access through Excel, and there's also online calculators that we could use to do this as well. Okay, so let's take a break for about 10 minutes. See you guys shortly. Okay, guys, we're back online. And I'd like to go through, so you guys, how many of you guys remember what a Venn diagram was? VENN. Does that ring a bell for you guys at all?
Two circles that overlap.
Bingo, exactly right, exactly right. And let me pull up a piece of paper here. Okay, they represent the probabilities of things occurring. Right? So, for instance, let's see, these are two things you might have. Each circle might represent the probability of being, let's say, probability of being male and probability of being female, right? You wanted it. There's no intersection between those. I'm talking in general now. I'm not getting into issues over gender identity and stuff like that. But you're either male or you're female, typically, right? So there's no overlap in them. You're one or the other. They're independent of each other. Now there are certain things that, for instance, you could be male and you could be left-handed, right? So here are all the people that are left-handed, and here are all the people that are male, and you could have the intersection of two of them. These are people that are both male and left-handed. You could be female and left-handed, right? So you have the intersection of the two of them. So you could have the union of two groups. In other words, two groups would be independent. You could have the intersection. You have a situation where both conditions are satisfied. And you can also have situations where, for instance, where you are male and you are let's see, um, you are greater than 6 feet tall, let's say, and in this case we could include both of these, which would include all everybody that's male and everybody that's 6 feet tall, and that would be the union of these two probabilities. I'm going to instead of beating this to death with my hoarse voice, which is getting hoarser as the night goes on, I'm going to play. I'm going to stand on the shoulder of giants. Okay, I'm going to play a recording from Levi Waldron, a lecture that one of his lectures. He's kind of standing on the shoulders of giants. He is tall, maybe not a giant, but he is tall. So I'm going to play a video recording of one of his lectures. The portion of now, notice I've put up here some of my lectures, previous lectures, and exercises and stuff like that, recordings of them. I will at the top of session 3 have a recording of our session, so you can get to our session. But I'm leaving up here, and again, it's voluntary. You don't have to watch these if you don't want to. Other versions of this same lecture that I've given or other people have given and so on, if you want to watch it again in another voice. But I'm going to play his voice for the description of these, using these Venn diagrams to describe certain probabilities. Okay, so I'm going to play this. Hopefully you'll be able to watch it and hear it online as well. Worst case, this starts in this part 2 lecture, right? It starts at about 36 minutes in. If you want to scrub, you can always scrub it. Just grab that and move it up and down, so you don't have to watch the whole thing if you don't want to. But it starts at about 36 minutes in. I'm going to go ahead and play that. We're going to watch this together.
And we can calculate those relationships, but you need to know a bit of probability notation. So remember, events, these are observable things with an observable outcome, such as having cancer. And if A and B are two different ones, the key notation I want you to know are the union, looks like a U, the intersection, the upside down U. The complement, which is not A, so if A is having cancer, then A complement is not having cancer. With the sum of these two always being 1, because you have to either the event has to occur or not occur, even if it's something where there are many alternatives, such as like rolling a dice, where if A is rolling a 1, then A complement would be rolling a 2 through 6. So it is everything else besides this one event that might happen. And one more that's really important for what we're covering today, the conditional probability, which is notated by a little vertical sign like this, sometimes called a pipe, but it's used for conditional probability. So it's the probability of A conditional on B already having happened. So the probability of A conditional on B, it means you assume that B has already happened and then ask what is the probability of A, conditional probability. It's nice to represent these as Venn diagrams where each event is a circle, and the area inside the circle represents a probability, and then an intersection can be represented as the overlap between these circles. And you can do this for 2 events, 3 events. You can draw Venn diagrams for up to quite a few events. But here in the middle, you see that this probability is A intersection with B intersection with C. All right, a couple little interactive questions for you. Please join in online too. How would you write down this probability shown in the Venn diagram in number 1?
You guys we can stop here, and if you want, give us a guess. What is that? If you can see that, what is that? What does that probability represent? It's going to be a simple one, real simple one. Yeah. Well, hang on a second. It's just the probability of B, right? It's just the likelihood of B occurring. Hang on, I'll play it now.
What's that? In number 1?
Yeah. That upper left-hand corner.
Doesn't look to me like it depends on A at all.
Right, just B.
It's just probability of B. Yeah. Yeah.
Okay, it happens to have some overlap with. Did I do that? Oh, that's Levi doing that.
And let's see if I can. Probability. I forgot to bring my my writing tablet. So that's the probability of B. Very good online, folks. You got it. Probability of B. What area between though? Well, what about that area in between? So that's not considered to be a intersection B. The rest of it is highlighted. Well, it's a good point. So there are actually other ways that this could be written. Probability of B is the simplest way to write it. But another way we could think about it would be, let's see, this part in the
probability of B minus the intersection of A of B and A plus the intersection of B and A.
So this part here,
I think you should just stick with the probability of B. I think Levi would have been better off not beating this to death.
Actually, that's a question down here. This is the probability of B intersection with a complement, right? So it has to be in B, and it has to not be in A. And this
Plus,
one here, number 6, what can we call this?
Oops, we're going down here.
What's that?
What do you guys think of that, of number 6 down here?
Yeah,
A overlap.
Intersection B.
Right, get that right, because it's the
so this kind of
both of them overlapping.
That gives a clue as to another much more complicated way we could have given the answer to 1, right? Because it's kind of the sum of these bottom 2. It's like the union of those 2. So we could have written the answer to 1 as the probability of B intersected with A complement, and then intersected with the probability of A intersect B, if you wanted to be complicated.
Don't worry about it. Don't get it that complicated. Just
but it
remember
also
that as the probability of B.
Okay, quickly, number 2.
Okay, what do you guys think for number 2? What is that? It's both of them. That's the union, right? That's the probability of A, a union B. Good. Thank you, Ange. Right? Union means it could be either. Right? Intersection means it has to be both. Right? So this is intersection. That's both A. Everybody that's in that overlap is both A and B at the same time. Whoops, I think
I like how online I can see that the B closed bracket turns into someone with sunglasses. Google Chat, the emoticons are not built around probabilities. Oh, so, okay, sorry. So what is something for? Yeah, I see a right answer online. What is number 2? A union B. Yep. Number 3.
Okay, that should be simple, right?
Just A, and number 4.
That's going to be a little bit more interesting.
Well, just a sec. I heard a lot of different things. It's getting more complicated now. What was yours? Yeah. Yes. A intersect with B complement. Maybe I'll spare you writing it out.
B complement does not B. So it's A, but all of the parts of A that are not B.
A intersection
with not B.
B
complement.
Okay,
a little bit funky, right?
You guys are probability
You
pros.
have this to go back to. There's a problem that involves these Venn diagrams, not quite as complicated
so why wouldn't it
in
be
assignment 2.
Complement? That would also include all this stuff out here.
You also can find some references online that'll help you interpret.
It's everywhere outside of B. Okay. But here it has to be outside of B and it has to be inside of A. So it's the intersection of A with
A, intersection of not B.
So we're like looking at these 2 events inside, just like a greater scheme of other events. There's like a C and D.
If we had a crowd, if you people all came in here one day,
but
we'd have a little bit more interaction here than we have now.
You know, with A, one outcome is that
Does that make sense to you, Brian?
Is that A occurs, and the other one is that it doesn't occur. So whatever it is, we don't have to have. So let's say here, these are 2 events. Each of them has one outcome that's represented by the Venn diagram, and then everything else. So this could be, say, A is having cancer, B is having diabetes. Then this would be the probability of having cancer, but not diabetes.
Some B is not just probability of B, because some B is not. Well, it's only B, but not all B's.
Yeah.
See, it's the probability of B intersection, not A. In other words,
that's right. This is number 6 is A intersection B, and number 2 is A union B. Yeah. So A is having either cancer or diabetes, and 6 is being very unlucky and having both.
Right, and that's the intersection. In other words, having cancer, having diabetes, and these people in the middle here on both. And that's the intersection. That you're satisfied.
All right. So if we have, if these 2 events are mutually exclusive, such as having chlamydia or not having chlamydia, then there's no overlap in the Venn diagram. And we can write that out by saying that the union of the 2 is just the sum of those 2 probabilities, because there's no overlap. If there was overlap, would that union, this probability of the first event union with the second, would it be more or less than in this case?
More, right? Because you're adding them together. It's always going to be more.
So the question is, this is the probability of the union for mutually exclusive events. If they're not mutually exclusive, would it be more or less than this?
If they're not mutually exclusive, that means they could have overlap.
Yeah, if they're not exclusive.
Yeah. Right. Well, what's the probability of chlamydia and not chlamydia is 1. It's all possibilities, one or the other. So it adds up to 1. But if they're not mutually exclusive, you could have people that, for instance, if one is chlamydia and the other is heart disease, you could have people that don't have that have chlamydia or have heart disease.
I'm not sure I'm following, but let me explain a little bit more. So the probability of the union of these two events, so this would be the probability of either having chlamydia or not having chlamydia is just the sum of those two events. If they were not mutually exclusive, there would be overlap here, and that probability would be less than what we write here because of that overlap. You wouldn't just add them because there's also probability that you have both.
If you include both, if it's exclusive, and you
in this case, because the options are exhaustive,
it adds up to 1. So it can't be a bigger
has to add up to 1. So there's only 2 outcomes.
You can never have a probability more than 1.
If this were ones and
one
twos on a
represents
dice,
all the possible probabilities.
they would still be mutually exclusive,
So
but not exhaustive.
Can't be more than 1. That's like having more than 100% of the outcomes. Don't worry about it.
And because they're exclusive, the probability of the
very
intersection
quickly, very brief part of this course. And it's a little tricky. And it's covered in the text also, so that might help also. So that goes for you guys online also.
Now, as soon as they're not exclusive, such as, say, having chlamydia or having heart disease, then we have this overlap. Okay, so there's some intersection of these two non-exclusive events. And as I mentioned, remember before we just added these two probabilities, if you just do that, you're counting this intersection twice, so you actually have to subtract it to correctly calculate the probability of this union. So your probability of having chlamydia and heart disease is your probability of each of them individually minus the probability of having both, so that you're not counting.
That person's already counted.
Those cases that have both
people
twice.
In the middle have already been counted. You don't want to count them twice.
Kind of makes sense. And this is an important rule. You can also write out the intersection as the product of these two probabilities if they are independent. So if having chlamydia and having heart disease are completely independent, having one does not increase your probability or decrease your probability of having the other, then the intersection of the two events, the probability of that is the product of the two individual probabilities.
I'll cut in here and I'll mention an example of that. Let's say that the probability that having heart disease and having chlamydia are independent events. There's no connection between the two of them. Then if the probability of having heart disease is 10% in a population, the probability of having chlamydia is 10%, but the probability of having both is 10% times 10%, or 1% is the probability of having both. However, there are going to be some situations where they're not independent. In other words, let's say you're looking at 2 venereal diseases. The probability of having chlamydia and having some other venereal disease. Well, a lot of times they're not independent. If you have one, you're more likely to have the other also. That's not independent. So that would be the first condition. And it wouldn't be just a simple multiplication. Okay, so, and again, I want to emphasize that this is a certain kind of notation that we're learning to describe the probability of events using these Venn diagrams. There's some questions on Blackboard in assignment 2, simple ones that you can put this to work on, you can play around with as well. And you might get like a couple of simple Venn diagrams on the first exam, not for a lot of points or anything like that. But once we move on from this, we're probably not going to come back to any of this. So I wouldn't get too worried about this stuff. I know this for a lot of students can be a little bit confusing, but I'll go ahead and continue. That formula looks familiar, doesn't it?
So the
conditional probability,
which I mentioned, is the probability of one event occurring conditional on the second one already having occurred. So So this is the probability of A conditional on B, and it's equal to the intersection of 2 divided by the probability of event B having occurred. So let's put this in some, I don't know, concrete example. If you're flipping a coin, your probability of having 2 heads in a row is 1 out of 4, but your probability of getting 2 heads conditional on the first flip already having been heads, you have to divide by the probability of that first event, and you get a half instead of a quarter. Or back in that example of heart disease and chlamydia, your probability of having heart disease, given that you have chlamydia, would be, obviously you have to have both of them, but since it's conditional on having chlamydia, you have to correct for the probability of that having happened. And here it's just written out in terms of the Venn diagrams. It's the intersection divided by the probability of the event that is on the right-hand side of the conditional sign. Yes?
I'll pause for a second. I'm glad I actually played Levi doing this, because now that you've totally confused about this, I can blame Levi instead of blaming myself. So maybe I'll find a better way to explain this. But again, I don't want you to freak out over this. I want you to, that first chart that you saw there that had the 6 different forms, if you can interpret those 6 forms, even if you just remember them, you know, then you'll be prepared for anything that's going to be on the homework or on the test or anything like that. So if you just go back over that part and look at how they would describe the intersection versus union and so on and so forth, then you're going to be in pretty good shape. But let me continue with this until we get done.
Probability of A and B is the same as the probability of A intersecting B.
Yes. Same thing. It means exactly the same thing. This is the probability of both events occurring. Yeah. I use and intersection interchangeably, just as I use union and or interchangeably. They mean the same thing.
Union means either could occur, and you're accepting either could occur. Intersection means both have to.
And this is going to bring us to Bayes' rule. And it's actually, given that equation on the previous page, it's a very simple derivation. It's just a basic rule of probability. And it comes from that rule and this observation that the intersection is commutative, that the probability of A and B is the same as the probability of B and A. The order there doesn't matter. Then we use that equation we had on the previous page just to expand this out, written in these 2 ways, as conditional probabilities.
He just substituted what he had in that other formula before.
By this probability of B, and we have here Bayes' rule.
Okay, now
and each of these terms.
If you look at this carefully, okay, what do we have here? We have probability of A given that B has occurred. Remember our diagnostic test? The probability of having the disease A, given that you've tested positive, B, given that B has occurred, a positive test. What is the probability that you actually have the disease, given that you have a positive test? And what was that equal to? It was equal to the probability of A, probability that you have the disease, the prevalence, times the probability of B, given that A has occurred. In other words, the probability that you test positive, given that you have the disease. That's the sensitivity, right? And over all of that is over, so that's the prevalence versus times the sensitivity over the probability of B, the probability that you test positive. Probability you test positive is the probability you test positive if you don't have the disease, in other words, true positives, and the probability of rather false positives, what's the probability you test positive if you don't have the disease. And that all really boils down to that formula that we had on the diagnostic test. So this Bayes rule, this conditional probability rule, is really the same rule that we learned with when we looked at the diagnostic testing, we looked at the positive predictive value.
Has their own terminology in Bayesian language, where this probability, this conditional probability on the left-hand side is the so-called posterior probability. This probability of A is the prior probability. The next term there is the likelihood, and that denominator is just like a normalizing factor. And this is very important for our calculations on screening tests and for interpretation. So when I was mentioning that if you go in for a prostate cancer screening test, what this is telling you, so this is, let's think of A as having prostate cancer and B being a positive test for the screening test. So then I would read this as your probability of having cancer given a positive screening test is equal to your probability of having cancer, your prior probability of having prostate cancer, that's the prevalence, the prior probability, times the probability of a positive test given that you have cancer. That is, we learned about that before. What's that called? Your probability of a positive test given that you have the disease. No, that's the sensitivity. Yeah, that's the sensitivity. So it's the prevalence, your prior probability, times the sensitivity divided by the probability of the prior probability of a positive test. So, and those will allow us to calculate the positive predictive value. Does the probability of A conditional on B equal the probability of B conditional on A? No.
If you need to change that into real words to really understand.
You're absolutely right. No, it doesn't. Only when the prior probabilities of those two things are the same. For example, the probability that you would retire given that you had as much money as Trump.
I want to stop you there. This was recorded before the man was president. I just want you to know that. Before he even was running for president. Is
that the same thing as the probability you would have as much money as Trump given that you retired? No. They're just different things.
That's an example of
what they would only be equal if the probability of you retiring is equal to the probability of you having as much money as Trump, which doesn't make any sense. Okay, so I think I'm going to skip over this because we're getting a little bit short on time, and
okay,
I do have
I'm going to stop it there.
Another example here.
Okay, we've kind of covered the diagnostic test and this contingency table before, but I wanted to give you another perspective on this idea of these Venn diagrams. I'm going to see, well, we stumbled a little bit on this. I wanted to comment on it as it was going through. But you can see it can get a little confusing. However, if we go back to that one table, I'll make sure a copy of that table is available, by the way. Yeah, find it again. Actually, I think I have a copy. I think there's on Blackboard, there is a copy of this PowerPoint. So you will have it anyway. Let me get to that table. Scroll. That's after this. That's after this. I think. Nope. Let me go back to that. There it is. I have a copy of this tape. I believe this copy. You have the PowerPoint. If not, I'll make sure there's a separate version of this so you can get a look at it, and I'll annotate it so it can make some sense to you. Okay, so how many of you got freaked out by this? Okay, did you kind of get the feel for this at least a little bit? And it really is a little challenging, I have to admit that. Because it's a little conceptual compared to a lot of what we 28%, 25%. Okay, that's better than 0%. I like that. That's good. Okay, so to finish up tonight, I want to show you that we can actually use Excel to do a lot of these calculations, as well as using the table that we have available, that Z table that we have available to us. And let me just go back here and get to that. I put a couple of files on here, including this one. I should have downloaded this. I don't want, oh, it'll open in Excel. Good. Okay, and this basically is a summary of 4 functions in Excel, which will help us do the calculations that we just described using the z-table. For instance, there's a function called norm sdist. Norm sdist. If you put in the z-value, it's going to give you to the area to the left of the z-value. Basically the same thing that we did when we were using the z-table. So I'll give you an example of that right now. Equals norm S, that's norm standard distribution, norm S dist, parentheses, and right now it's only, so you can see right there, it's waiting for the z-score. So if I put in a z-score of -1, anybody want to remind me of approximately what we would expect to the left of a z-score of -1? Yeah, about 16%, right? You guys agree online? And indeed, that's what we get. So it gives us that score. How about a z-score of +1? So equals norm S dist, parentheses, +1, right? What's going to be 16% on that side? It's going to be more like 84%, right? And indeed, it's about 84%. So norm S dist, basically you put in the z-score and you don't have to go, it gives you the result that you would get from that table, right? So that's another way of getting that. If I asked you what would be to the right of a z-score of 1, right? This is what would be to the left of it. What would be to the right of it? What would be to the right of it is equal to 1 minus that z-score, which is going to be our 15% at the upper end as well. So you can use that function, norm sdist. There's another one that doesn't have s in it. That norm sdist literally represents that table. Norm dist is a way for you to calculate what the actual value to the area to the left of the z-value for your x is equal to. Norm dist. This time when I put into parentheses, it's going to ask me for x, the mean, the standard deviation, and cumulative. Okay, let's see what that might mean. Let's think back to one of the examples that we had before. One of the examples was, for instance, let's say that you had teachers had a mean salary of $32,500. We're interested in what proportion of the teachers, what percentage of the teachers had salaries less than 28,000. Okay, so I can put in 28,000. It's always going to give me the area to the right, left of that. 28,000 is X. The mean was 32,500, comma. The standard deviation, what was it, 3,000 or something like that? It was 3,000. Oh, was it 32,000, not 35,000? Okay, good, thank you. Okay, and cumulative. Now, if I say false to that, it's only going to give me the area for that straight line that goes up and down. Basically meaningless. We're always going to say true. We always want the area to the left of that. Why it even asks you for cumulative to say true or false, I have no idea, because just saying false is really basically meaningless, because that area, that area, 28,000, that straight line that represents 28,000 has no area really anyway. Straight lines don't have an area. So this would give you the area to the left of 28,000. So it's not, remember that was the answer we got, about a little over 9% of the teachers had that salary. So that gives you a way to find the p-value, the proportion, without even bothering to calculate the z-score. That was norm s-dist. Well, how about norm inverse? Remember the problem we just had where we had the percentage, the area, but we didn't know what the value was? That's where we're going to use norm inverse. Okay, so let's see how that works. Equals norm inverse, parentheses. It's asking me for the probability. Remember the problem we had where we wanted to predict what blood pressure represented the top 10% of the population. So since we always work to the bottom, the probability to the left, the probability to the left of this value is 0.90, comma, The mean, I think, was 120, and the standard deviation was 8, right? I'm going to close that, and it should give me a value that represents the blood pressure that has 90% below that and 10% of the population above that. And it was 130, or a little over 130, the same as we calculated using the table. And norm S inverse is just simply, if I was going to do the same thing for that top 10%, I want to know what the z-score that would represent that top 10%, I could use equals norm S inverse, parentheses, and it just wants the probability, like the one we just did was 0.9. What is the z-score that represents 90% below, 90% of the distribution below that point? And the z-score is a z-score of 1.28, right? If I had said equals norm S inverse, parentheses, and I was looking for the bottom 2.5%, right? It was going to be 0.025. That's going to represent roughly about a z-score of negative 1.96, or in other words, -2, right? 2 standard deviations below the mean represents about 2.5% of the distribution, right? So that's how we got that. Okay, so that gives you a tool that gives you 4 tools that you could use the Excel instead of tracking down a table to do these calculations. I could add to this our tool for binomial distribution, which is equal to binom dist, right? Parentheses, and you would put in the number of successes, number of trials, the probability, and whether or not you wanted a cumulative or you just wanted that exact outcome. You would say true for cumulative if you wanted, say, the probability of 2 out of 10 or lower to 1, 2, 1, and 0. Don't forget 0 counts, right? 0 counts also as a possible outcome. So that would give you the cumulative probability of getting 2 out of 10, 1 out of 10, and 0 out of 10. Okay. On the other hand, if you wanted the probability above 2, you would calculate the probability for 2 and subtract it from 1. That will leave the probability for 3 out of 10, 4 out of 10, 5 out of 10, and so on and so forth. You could use it that way. Now, just one little tricky thing, last little tricky thing that I want to bring up with you is, what if I asked you, what is the probability of having at least one out of, in the example that we did before, I'm going to make a new one up. 10% of the population is diabetic. I'm going to sample 10 random people from that population. What's the probability that I will have at least one person that is diabetic? What's that probability, right? Let's think about that. What will satisfy that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 will satisfy that. What doesn't satisfy it? 0. So I do equals binom dist, the probability of getting 0 successes, comma, out of 10 trials, comma, 0.1 probability, comma. I could put true or false here. I'll get the same thing because there isn't anything below 0. So I'm just going to put true just for the hell of it. So now that's the probability of getting 0. Probability of getting 1 or more is equal to 1 minus the probability of 0. Okay, another tricky one. What's the probability of getting? Let's see. More than one person that's diabetic. If I sample 10 people from this population, more than one is going to be 2, 3, 4, 5, 6, right? So we can only go down. So I want to know the probability of getting 1 or 0 and subtract that from 1 in order to get the probability for 2, 3, 4, 5 equals binom dist, parentheses, and I'm going to put in 1, comma, 10, comma, 0.1, comma, true, so it includes 0 also. That's the probability of getting 1 or 0, 1 or 0, and the probability of getting more than 1 is equal, in other words, 2 and up, is going to be equal to 1 minus that. Okay, so it can get a little bit tricky. It's got a little bit of wordcraft in here, a little bit of what they call computer programmers and grammatricians, people that study grammar. They call parsing, right? You got to like read the sentence, read the question, and break it down and understand what they're actually asking. Break it down into its parts and understand it. Am I muted? I don't think I'm muted. I should be not muted. I should be back. Oh, okay, good. It's probably a little glitch in the internet or something like that. Good. So at any rate, it'd probably be okay on the recording, but hopefully I wasn't silent for too long. Okay. So at any rate, so that's I think where we stand. We're almost at about 8:20, so I think now's a good time to actually tell you the truth. Legally, I'm required to release you at this stage. So you guys, hopefully this isn't too confusing. And thank you very much, most of you, for getting assignment number 1 in on time, at least attempting it on time. Anytime you want now, you can go back and you can work on it further. It takes me a little bit a few days for me to grade assignment 1 because I got to open every file, that Excel file, the SPSS, the Word documents. You upload, I have to upload them and take a look at them. So it takes me a little while to grade that one. In the future, the homeworks get graded much quicker because usually you answer the questions. They're 90% self-grading. All I need to do is every once in a while go through them to make sure that there's no glitches. So for instance, if it's not clear on the question whether you should answer with a percentage or a proportion, and you answer it a way that the machine's not thinking, you should answer it. I go back and look through all the wrong answers to make sure that they're graded correctly. Now, I believe on Wednesday we have another class, and if I'm not mistaken, on Monday of next week, we have our first exam. Am I right about that? And our first exam is not going to cover a ton of material, right? It's just going to cover where we covered up to this point. And the way the exam is going to work, it's going to be online, okay? The exam is going to be online. It's an open book exam. Anything's on Blackboard, any of the text material and so on and so forth. I prefer you not go like, it doesn't include like Googling answers and stuff like that, but work from the materials that you have. It's strictly online. You will have 2 opportunities to take the exam. You'll have about approximately 3 or 4 days for you to do the exam. We'll give you a window of 3 or 4 days. Once you start the exam, sit down, start the exam, you'll have 3 hours in that sitting to complete the exam. And then if you don't submit it yourself, it'll automatically submit. When you're done with it, it will tell you, and if you don't know how to do this, you should, at some point, we'll discuss this, but you should figure out how to do it. If you go to the grade center, it will tell you which questions you got wrong. It will not give you the answers. You then have a second chance to take the exam and to see if you can't do better, considering which ones you got wrong. So you got 2 shots at the exam. Each one is a 3-hour sitting, and each of them is open booked on this first exam. So I want you guys to not freak out over this first exam because it's going to be limited amount of material very early in the semester. I know some of you guys, because of delays in your joining the class, are just catching up to us. So I don't want you to freak out and stuff like that on this, but you have a lot of opportunity on this to kind of do decently well on the exam. And remember, those homework assignments, they're 40% of your grade. If you get 100% on it, if you go back and redo them, you get 100% on them. The homework assignments, the exam, similar to homework assignments, unfortunately, Blackboard will not allow you to just open up your old version that you submitted and modify it. You're going to have to start from scratch when you take it the second time, and you won't have those answers in front of you. You might want to save a copy of your submission, or write down your answers or something like that, so you know what you did the last time around. So on the answers that you got right, you don't have to waste a lot of time like redoing them and so on. So I think that's more than fair, and I think that's a good way for you to get introduced to taking an exam in this course. For a lot of you guys, might be the first math course or the first graduate course or the first class you've taken of any kind in a long time. So we're easing you into this. Okay, so I'll put up the rules. Let me just check to make sure that I got the timing right on the syllabus. I tend to drift a little bit away from the syllabus. on some of this stuff because I always am kind of trying to be sensitive to what you guys how quickly you're picking stuff up and how the class is progressing. Let's see, June 13th. Oh no, I'm wrong about that. It's June 20th. Never mind. Okay, it's June 20th. We have another few sessions where we're going to be winding up and doing some more stuff. We're actually a little ahead of where we would normally be. Actually, I'm glad we are, because that will give us 2 sessions to more than one session, 1.5 sessions maybe, to look at sampling distributions and central limit theorem and something called confidence intervals, right? So that'll give us a chance to really get to understand that a little bit better before you take that first exam. So the first exam's on not this week, not next week rather. It's on the 20th, which is a Monday. Is that a Monday or a Wednesday? That's a Wednesday. That'll be Wednesday. So you're going to have the whole weekend. You'll have till at least Sunday night to submit that. Okay. Now I'll post a bulletin forum on the discussions board. So if there's any questions, like Tony, you put the wrong president's file up, which I got a lot of, right? You can post that to the discussions board. I can comment and let you know what to do about that question or clarify a question or something like that. And it's a place where all of you can go to the discussions board and see if I've made any clarifications to be fair, so everyone gets the same explanation. It'd be much better to do that way than for you to email me individually on questions on the exam. Just go to the discussions board, post your question, and go there every once in a while just to see if anybody's posted, asked for clarification and something that you would benefit from as well. Okay, so have a good night, guys. Go